Previously in this week, we have discussed the theory as well as how to implement simple linear regression. How can we quantify the quality of our regression? And finally, we have used the theory of simple linear regression in a dataset of practical importance. In this entire discussion, we have assumed that we have one regressor or independent variable x, and that is connected to one output, that is our response of y. X and y are related through a linear relationship such as w0 plus w1x equals y. Now in reality, we will find many cases where certain response variable depends on more than one independent variable. For instance, if we think about the example problems that we were dealing with, where the age of a propellant influences its strength. But if you think about, age is not the only factor that determines the propellant strength. How we store the propellant, that says a lot about the propellant strength. For instance, what is the temperature of storage of the propellant? That will obviously influence the strength of the propellant. Therefore, we can identify at least two variables, temperature of storage as well as age, which are independent variable, and it will influence the dependent variable, that is the strength of the propellant. Problems like this cannot be dealt with the theory of simple linear regression. We'll now get into multiple linear regression, where we will have more than one independent variable or more than one regressors, or we have a vector regressor. A vector can have many components. For simplicity, we are still keeping this relationship between the regressor and the response to be linear, but we will have more than one independent variable. So let us see how we can do it. Earlier, we were discussing about using this training dataset T, xi, yi, where I goes from 1 to n, to get a regression fit, that is an approximation of y hat is equal to w0 plus w1x. Now, as we have discussed, in reality, most problem you will find that they have multiple regressors. In case of multiple regressors, the training dataset will look something like this. Each data I will have x1, x2, etc. up to xk, all at I, and yi. That means x1, x2 up to xk, they are my regressor, they are the independent variable, and y is my dependent variable or the response. So at every experiment, I have this k number of independent variable that I can control, and I can measure the corresponding y. Y is still one number, but x has many numbers now. So now we have our regressors, k number of regressors from x1 to xk. Now we'll develop this multiple linear regression model, which will learn with two or more regressors. So let us start with a case of 2. That would be the easiest extension of simple linear regression. In this case, our dataset will have xi1, xi2, yi, I goes from 1 to n, and our regressors are x1 and x2. Now we assume a linear model, just like the previous one. So our model is that y hat, that is the estimation of y, is equal to w0, that is our bias, and we have two weights now, one for x1, one for x2. So I have w1 x1 and w2 x2. So goal is obviously to minimize the cost function, that is E, but E is now a function of three variables, w0, w1 and w2, and the expression of E is given by 1 by n summation of y minus y hat, and this y hat is w0, W1 x1, W2 x2, and we will sum over I data set. So I am writing all this x as xij. J gives the regressor, which regressor we are talking about, and I gives the experiment that we have done, that experiment number or test number. So now our goal is obviously to minimize this least square cost function, and from there we'll get the expression of W0, W1 and W2. So let us take this del E del W0, which will be 0. To take the derivative of this right hand side, derivative doesn't do anything to 1 upon n, doesn't do anything to summation. The square will now become 2 multiplied by whatever there in the first bracket, and then I am taking the derivative with respect to W0. I have only this negative W0 here. So if I take the derivative, that will bring only -1. Therefore, this 2 minus 2 is coming here, multiplied by whatever there in the first bracket, and the square will go away. So the derivative turns out to be -2 by n, and whatever there in the first bracket, summation of that, the square is now removed. Similarly, we can find out the expression for del E del W1. It will also give us this -2 by n and this first bracket. But then we are taking with respect to W1, therefore this xi1 will come with this, will be multiplied with this. So it turns out to be whatever there in the first bracket multiplied by xi1 summed over I equals 1 to n. Similarly, this del E del W2 will be given by, once again, -2 times m summation. Whatever there in the first bracket, it will stay, but then we have to take derivative over here. So instead of xi1 in this case, now it will come as xi2. So now we can see that we have 3 equations, so we can simplify a bit maybe. So here we can take this -2 by n out of the question, and we break this summation sign. So I have n W0, because this is summation of W0. So that will give me n of W0. Here W1 and summation of xi1, W2 summation of xi2. That gives us summation of yi. So that would be our one equation. Similarly, from here we have this W0, but now W0 is multiplied by xi1. So if I do the summation, it would be W0 multiplied by summation of xi1. W1 has xi1 multiplied by xi1. So W1 and summation of xi1 square. Then W2, where xi1 and xi2 are multiplied. So summation of xi1, xi2. And on the other side, I have xi1, y1. So this is xi1, y1 here. Now coming to the third one, here we will have W0 multiplied by the summation of xi2. W1 will come with xi1, xi2, and W2 will be with xi2 square. So the equation will come like this: W0 summation of xi2, W1 xi2 xi1, W2 xi2 square is equal to xi2 yi. Therefore, we now have 3 equations, and we have exactly 3 unknowns, this W0, W1 and W2. So we should be able to solve these 3 equations, and we'll get these 3 unknown W0, W1, W2. That solves our problem. Now you can see that if we set this x1 equals x and x2 equals x square, we'll be able to fit a polynomial of w0 w1x plus w2x squared type. Now this function looks nonlinear relationship between x and y, but then we can still use the procedure of linear regression to find this w0, w1 and w2. So a regression becomes linear when these equations, which are my normal equations, which means the equations from which I evaluate this regression coefficient, as long as those equations are linear, the regression becomes linear. Even though we are probably fitting y and x through a nonlinear relationship. Let us now generalize this idea with k regressors, where k goes between 0 to 1. For k being 1 or 2, this is within the realm of simple linear regression. When k becomes 3, that is the case we have just discussed. And when it becomes more than 3 or maybe large in number, for some practical problems, k may go in hundreds or even thousands. So for such cases, we need a general relationship. So for instance, we take here the model, which is again linear model, y hat is equal to w0 plus w1 x1, w2 x2, all the way up to wk xk. So now we have unknowns from w0 to wk, total k plus 1 unknowns. Here I am running my experiments. My experiment index is I, and here this I goes from 1 to n number of experiments I am running, and response is also a real number, a scalar, that I am getting y1, y2, etc. up to yn, every experiment giving me some value of the response. The regressor, of course, it is giving me, for experiment 1, it is x11, x12 up to x1k. Experiment 2, it is x21, x22 up to x2k. For experiment n, it is xn1, xn2 up to xnk. So essentially, in regressor, here these data points, you can say that they are xij, where this I is coming from the experiment number, and j is the particular regressor we are identifying with j. So this is my total data set in this table, and we have to see that from using this data set, how we can find out some expression w0, w1, w2, etc. up to wk. Now for I equals 1 to n, I can write that this yi or y hat I will be equal to w0, w1 xi1, w2 xi to this I coming from experiment, and 1, 2, etc. they are identifying the particular regressor or particular independent variable. So it goes up to wk xik, and then I can write it succinctly using a summation sign. This is w0, wj xij. So this j is identifying that particular independent variable, and I is identifying the particular experiment. Therefore, we are interested now to minimize the least square cost function. Here the least square cost function E will depend on w0, w1, etc. all the way up to wk, k plus 1 independent variable, and this is again 1 by n summation of yi minus y hat I whole square. This is my y hat I, this part, whole square of that. So now the goal is to take the derivative of E with respect to each of this independent variable, starting from w0 all the way up to wk. So if I take it with respect to W naught and I set it to be 0, the derivative is, of course, as we have seen earlier, as I take the derivative, 2 will come out because of this square. And then with respect to W naught, I have negative W naught inside. So it will bring a minus sign here. So minus 2 by n, and whatever there in the first bracket, it will remain there. Only the square will go away. So that gives me del E del W naught. Similarly, I can take derivative with respect to W1, W2 or WK in general. So let us say I write this is del E del WP, where P goes from 1 to K. And what will happen here is that minus 2 by n will come here. Whatever there within the first bracket will come here. And then this particular WP should be related to XIP, because that is what is multiplied. You can see W2 is multiplied with XI2, W1 is multiplied with XI1, WK is multiplied with XIK. So WP have the corresponding XIP. I am not using J here because here I am summing over J, and again J goes from 1 to K. That would be confusing. So that is why I am bringing another index P. Now you see that here I have one equation and here I have K equations. Together we have total K plus 1 equations, and we have the unknowns from W naught to WK. We have K plus 1 unknown. So in principle, we should be able to solve them and get the values of all these unknowns. So now let us see how we'll get the equations of W naught to WK. So the first one is coming from del E del W naught. Here I can write by breaking this summation into each term, and I am removing this 2 by n, only minus sign I am keeping. So I will have this n W naught here, because W naught will come out of summation sign. Summation will be only over 1. So this is n W naught plus W1. That will give us this Ij. So this Xi1 will be summed over. Then W2 will come as Xi2. Then up to WK summed over Xik. And on the other side, we will have summation of Yi. So this equation comes from here. Here this summation J1 to K, I have broken them in this series of terms. So you can see this is a linear equation of unknowns are W0, W1, W2, etc., etc. Even though it looks complicated, it is still a linear equation. Similarly, I can take here, for instance, P equals 1, and I can write the equation setting del E del W1 to be equal to 0. If I do so, what will happen is this Yi will be multiplied by Xip, and in this case P equals 1. Therefore, Yi is multiplied by Xi1. It goes on the right hand side. On the left hand side, I have W0 multiplied by Xip, P equals 1. So summation of Xi1, W1, then Xi1 will be multiplied. So Xi1 square, then W2. Xi2 was already there, as you can see here. Now it is multiplied by Xi1. Similarly, Xik, which was already there, it is multiplied by Xi1. This goes my second equation. Similarly, I can take this, let us say, P equals 2, then W0 will be multiplied by summation of Xip, P is 2, so Xi2. W1, Xi1 was already there, it is multiplied by Xi2. W2, Xi2 was there, so Xi2 square. etc. up to wk. xik was already there, multiplied by xi2, and on the right hand side xi2 is multiplied with y1, and we have taken the summation. We can go like this. The last equation will be w naught. Here p equals k. So xip is now xik, and w1 multiplied by xi1, xik, w2, xi2, xik, etc. The last one, it has xik before. So now it has xik whole square. Right hand side is xik multiplied by yi, summation of that. So together you can see that here I have one equation and then p1 to k. So total k plus 1 equations I have. All the equations are linear equations. This is a linear regression, no matter how you can express x1 or x2. And we can solve this equation. In principle, solving will not be easy if k is large, but in principle we can solve them and get the values of the unknown w0 to wk, k plus 1 values. In fact, the goal is that if k is large, then solving these equations in an easier manner, that should be the goal now. And also, if we can have a compact notation to write these equations, that would be even helpful. So let us see if we can make this notation any better. So for instance, here, if I take this and write in the way of we were writing in terms of averages, bars, if we write that way, then we can have, for instance, here daily del w naught. I can write this as y bar. This is 1 upon n yi summation, that is the bar y bar, and then 1 upon n w naught summation, that is simply w naught because n cancels out. And here I have this xij will be summed over. It will give me xj because it is summed over all I. This is the bar of xj. And then j equals 1 to k number of such terms will come. Similarly here, if I look at this daily del wp equals 0 in this equation, and I bring this average sign, the first term will be xip, and that will give me this pth x with yi. It would be summed over, so it will give me this xp y bar, then xp y w naught. xpy is bar here, and in the same way the last term will be wj xj xp bar. Wj is not really average. This is here wj doesn't come here. It is only we are summing over I. So xij xip, that multiplication, that product is summed over an average. So this is an average of xj xp. If I now take this and write all the equations for p equals 1 to k, this will give one equation, this will give k equation. Once again, we will get the same equations, k plus 1 equations, but it may look slightly better here. So this is w0 plus w1 x1 plus w2 x2. I am breaking up this one. This equation is coming from here. w0 is here. w1 x1 bar, w2 x2 bar, etc. up to wk xk bar equals y bar. First equation. In second equation, this x1 will come. This is p equals 1. So I have this x1 bar into w0, x1 square bar, w1, x1 x2 w2, up to x1 xk bar, wk is x1 y bar. Similarly, I can take p equals 2, that is x1 will be replaced by x2 here. So I have x2, here I'll have x2 x1, here I'll have x2 square, here I'll have x2 xk, and here I'll have x2 y average of that. And finally, we can go this way. This would be P equals K, xk average, xk x1, xk x2, etc., etc., xk square, and xk y. So here the equation looks slightly cleaner, but it doesn't help in any other manner. You have to solve these equations anyway, and the symbols are now slightly smaller. That is why it looks cleaner, but it has no other advantage than the previous one. But this kind of equations, instead of writing this way, if we write it in vector matrix form, Ax equals B type form, then it will look much cleaner, and it will also help us to understand this problem, solve this problem more efficiently. How we'll do that, we'll see that in subsequent lectures. Now, to summarize, we have discussed here the theory of multiple linear regression, fitting a polynomial as well as several other complicated functions may be posed as a problem of multiple linear regression. For instance, if I have a problem of y equals x plus log of x plus root over x plus tan of x, you can see that the function here is nonlinear. The relation between x and y is nonlinear, but you can take this as my x1, this is my x2, this is my x3, this is my x4, and then you can take it as a multiple linear regression problem. So, fitting a polynomial as well as many other functions, we can use this multiple linear regression theory. So, even though it looks simple, its application is huge. For your exercise, you derive the normal equations. Normal equations means the equations for the unknown. In this case, the unknowns are W0, W1, W2, three unknowns. For the least square regression of this xi, yi type data that goes between I equals 1 to n. Use this technique of multiple linear regression. Even though it looked nonlinear, the theory of multiple linear regression will be applicable here. So that's all for this lecture. Thank you, and I'll see you in next class.